Hello everyone and welcome to the new simulation at the speed of design session. In this particular session we will talk about Altair Inspirecast, and I will give you a full demo on how to make use of the simulation to improve our designs. The idea is to start bringing the design part, into the platform to analyze. The first thing we will analyze is where we can place the gate. It's the first thing we will think. Okay, so where we can place a gate, we cannot place a gate. We will do a thickness analysis that will help us to, once we identify the best region to place the gate, we will make sure that the thickness is appropriate for the gate location. After that, I will understand how the part will be allocated in the mold and regarding to gravity direction, and then we will start with the setup. We will do a very quick setup for the first iteration, so the only thing I will define is the material I will use, and I will place a first initial guess for the gate location and size. So I will start with the gate at the center of the part, let's say 2 millimeters height and 40 millimeters wide. And as I said, this is the initial guess, and it's just to run the first iteration and to get some information about the evolution of the process. So next thing we will do is to define the velocity at the gate. We will use 30 meters by second. And after that, we are ready to run the first simulation. We will use a virtual mold, run only feeding analysis, just to go very quickly and get some results to start designing our process based on the information that the simulation provides. I have this example already running my computer, so let me load the results. This case may take 10 minutes to run the entire feeding analysis. So let's analyze the initial results. So as you can see, we can visualize the feeding evolution of the material combined with the temperature, and we can start understanding some issues such as unbalanced feeding, air entrapment near the gate, and pressure peaks also near the gate due to these entrapments. These entrapments will be very difficult to remove because they are very close to the gate at the last stage of the feeding. So this is a critical issue, and we must solve this probably changing the feeding pattern. One thing that we can do is to try a different configuration. For example, using one gate at the right-hand side location, another gate at the right-hand side but more central in the central position, and another gate at the left-hand side of the center of the part. With these new gates, we will try to balance the feeding, and we will try to push the material where we need to be pushed. Okay, so let me start with the center gate oriented to the right. We will create a 20 millimeters by 2 millimeters gate, 50 millimeters. Okay, and as you can see, I'm orienting the gate to the right hand side to force the material to go on this direction. We will do the same thing with the other gate at the right, okay, 20 by 5, and orienting the gate to the right hand side. And we will create the final gate on the left hand side to fulfill the left side of the part. So in this manner, we can distribute the material as we need, and we can do a lot of iterations, we can do a lot of tests. As you can see, it's very easy to redefine gates, to move around gates, and to create new gates just to achieve our goals. So let's see what happened with this new gate configuration. So as you can see, the feeling is much more balanced. You will see on the animation that the right hand side of the part is filled at the same time that the left hand side of the part. This is extremely important to keep air entrapment control to keep pressure balanced. As you can see, the pressure decreased quite a lot on the right hand side of the part. And of course, if we analyze the material tracking, you can see that I am filling the right hand side of the part with the two gates I set on the right hand side and the left hand side of the part with the gate I set on the left hand side. So based on this configuration, we can create our runners, the entire runner system. We can mirror the part, we can place the two parts in the mold, and we can go and run the complete simulation considering the piston velocity, the piston phase change, and every single parameter that we will set up on the machine. So let's see how the filling looks like right now with the runners and the two parts. We cannot expect many differences in comparison with the solid gates, but we can see some small changes on the filling of the part. Very important, we will identify very easily entrapments, and we see two particular regions. After the holes, you can see that there are some air entrapment, and these will be very difficult to avoid. So one thing we can do is to remove the holes from the part, and we can create the holes after manufacturing, so as a post-process. But by removing these two holes, we will avoid a lot of rejections or a lot of defects on our parts. Inspire has a lot of tools for geometry addition or geometry creation. If we want to move the holes, create new holes, or remove the holes, we have a lot of great tools that will help you in these tasks. So once we remove the holes, we can run a new iteration to understand what is the behavior of the flow pattern. Now without holes, as you can see on the left hand side, the filling is almost perfect. There's no air entrapment on the left hand side. The material flows perfectly from the gate to the end of the part. In the center part, also we have some air entrapment. In the right hand side, sorry, we have some air entrapment that we will need to solve with some overflows. But as it is close to the walls, maybe we can put some overflows there to remove this entrapment. So this is what I will do now. I will bring overflows that I have designed in other applications. We can do that. We can design in InspireCast, or we can design in other applications and import the geometry, and then we can designate this geometry as overflows, for example. So once I define the overflows, I will run a new iteration. Remember, these overflows have been created without any information, just experienced. So what we will do now is to combine experienced with information. So let's see how these overflows are working, and let's see how we can use the simulation to improve our experience and designs. Okay. So as you will see, most of the overflows are working fine. On the left-hand side, the overflow is capturing all the oxides and entrapment that I can generate due to this square hole. But you will notice that in the center part, for example, the center overflow, this one here, is working pretty fine, catching up all the air. But in the right-hand side, we may have an issue. This air entrapment is far away from the overflow entrance. So probably we will have some entrapment. What can we do? Well, basically, we must move the overflow. And this is extremely easy and simple to do in InspireCast. So basically, you grab the overflow, you use our move tools, and you reposition the overflow close to the required area. So you can see how easy it is to modify the overflows, and all our geometry is parametric. So every change I am doing right now, I can control later on using some parameters, okay? And basically I can move the overflow just to position not only this overflow, but any part, any gate, any overflow. If I was setting some air vents or whatever, I can use the geometry tools to modify, edit, or create uh, new features. Okay. So once we have modified the overflow again, let's run a new iteration. Remember, we already ran 5 iterations. In each iteration, I implement some changes, and now you will see the material flows tends to move the air to the new overflow position. So the advantage of simulating during the design is that we can improve the design based on the information we get from the simulation. And this is powerful for as a tool for designers and process designers. So just to conclude, on the right hand side, all the overflows are helping to remove the air and oxides from the parts. So now overflows are in their optimal positions. Okay, so what we will do now is to continue with our design process, and I will run a thermal simulation, a solidification analysis. The solidification will show us the solid fraction evolution, for example, how the material solidifies inside the mold, and this will be extremely useful to predict the porosity that will remain inside the part after production. So one thing we can do to remove porosity is to modify the cooling pattern. So we will create a mold, and once we have the mold, we will create some cooling lines to modify the, as I said, the cooling pattern of our parts based on the mold temperature. We have tools to create cooling lines, move cooling lines, modify the dimensions, coolant material, temperature of cooling lines, and everything, as I mentioned before, is parametrically controlled. So at any time, we can iterate, we can come back, modify a diameter, modify a temperature, modify a size of overflow to influence the solidification pattern or cooling pattern. Okay, so once I add the cooling lines, I will perform a new iteration to understand how the cooling pattern has changed now. So if we compare the porosity we have now with the total porosity we had without cooling lines, you will be able to see that the porosity size has been reduced and the porosity has been eliminated for some locations. Another extremely important thing is that we can analyze the evolution of the temperature in the mold to prevent thermal stress or to analyze the evolution of the temperature in the mold during the entire production cycle. Okay, so this is all we have for you today. I know this is a lot of information. I went very quickly, but I hope you enjoy and you get the necessary info to start using InspireCast in the simulation-driven design process. Thank you very much and see you next time.